A stone tower leans precariously, yet it has stood for 800 years. Modern engineering still cannot fully explain how. This is the enduring mystery of medieval construction. Today, we explore 25 medieval structures that actively defy our most advanced building methods. By the end, you will understand the lost principles that allowed these ancient masterpieces to outlast centuries. How did a cathedral built on a swamp remain perfectly level? What secret lies within a mortar that repairs itself? We will uncover the hidden intelligence in stone, wood, and water. What does true resilience look like when it's built by hand? Their genius was born from a paradox, a world of profound limitations that demanded limitless vision. A master builder of the era was not just an engineer but a philosopher of stone, a mathematician of the divine. His blueprints were not drawn on paper but encoded in sacred geometry, patterns believed to mirror the perfect order of creation itself. He worked with rules of thumb whispered from apprentice to master over generations, a living library of knowledge written in the scars of past collapses and the silent strength of what still stood. Every decision carried immense weight, for these were not merely buildings. They were acts of faith carved in rock, symbols of power meant to endure centuries of conflict and weather. The tools were simple, the materials local, the risks catastrophic. One miscalculation could mean not just financial ruin but a spiritual crisis, a fallen testament to human hubris. Yet from this pressure cooker of faith, ambition, and raw necessity emerged solutions so elegant they border on magic. This mindset, blending deep observation with deeper belief, is the key that unlocks the first of our 25 marvels. It begins not with a fortress or a cathedral, but with a simple, profound question answered in wood and water. How do you build a thriving city where there is no solid ground to stand on? The true defiance lies not in surviving the centuries, but in how these structures continue to ask questions we struggle to answer. To understand this, we must first define our terms. When we say a medieval creation defies modern engineering, we are not simply celebrating its old age or its artistic beauty. We are pointing to a specific, tangible puzzle. It is a structure that presents a genuine conundrum to contemporary science, a problem that resists easy explanation or straightforward replication under the same historical constraints. Think of it as a locked door from the past, and we are still searching for the right key. We judge this defiance by several key criteria. First are the structural mysteries, where the distribution of weight and forces seems to dance along the edge of known physics, creating a stability that our own calculations might not predict. Second are the material enigmas, the mortars, concretes, and metal alloys that possess a durability or even self-healing property we cannot economically reproduce today. Third is the sheer audacity of construction logistics, projects of monumental scale and precision that appear logistically impossible with the era's documented technology and manpower. And finally, there are the achieved properties, whether acoustic perfection in a hall or an optical illusion in a spire, crafted without the underlying scientific theory we take for granted. This framework is crucial. It moves us beyond simply admiring old buildings and into the realm of active investigation. Each entry on our list is not a relic to be dusted off, but a living challenge to our understanding. It is an invitation to look closer, to wonder how, and to appreciate that the builders of the medieval world possessed a deep, intuitive mastery of their environment that sometimes still outpaces our own analytical tools. With this lens in place, we can begin our journey to the first site, a place where the very ground refused to cooperate, and the builders responded with a breathtaking act of defiance. Beneath the bustling streets of modern Istanbul lies a silent, drowned forest. The Cistern of Theodosius, built in the 5th century, is not a castle or a cathedral, but a cavernous reservoir designed to hold millions of gallons of fresh water. Its scale is the first whisper of defiance, a man-made underground lake supported by a seemingly endless grid of columns, each one salvaged from older, ruined temples. But the true engineering miracle is not what you see, it is what you do not see. Not a single drop of that ancient water supply, held against the constant push of the earth, has leaked out for over 1,500 years. This structure was built directly upon the soft, shifting substrate of a drained swamp, a foundation that modern engineers would consider a nightmare scenario, prone to settling and cracking. Yet the cistern's brick vaults and mortar have not just resisted collapse, they have maintained a perfect, waterproof seal through earthquakes, through the weight of a growing city above it, and through the relentless patience of time. How? The answer is a lost harmony between material and environment. The mortar itself is a mystery, likely incorporating local materials that allowed for a slight, flexible give, letting the structure breathe and settle as one cohesive unit rather than a rigid cage destined to fracture. Furthermore, the builders displayed a logistical genius that software would struggle to optimize today. They gathered hundreds of non-identical columns from various demolition sites, each with different heights and diameters, and then engineered a solution on the fly. They built adjustable stone bases and capitals to make every column fit perfectly under the ceiling, creating a uniform support grid from a chaotic assortment of parts. This is medieval engineering at its most profound, solving the fundamental problems of water pressure and unstable ground with a solution so elegant it remains functionally perfect to this day. It asks us a quiet, humbling question. If we built something today meant to last for 15 centuries, what forgotten wisdom would we need to rediscover? That waterproof harmony beneath Istanbul gives way to a symphony of light and stone in the French countryside. Chartres Cathedral is not merely a building, it is a structural paradox that continues to whisper its secrets. Its walls, stretching toward heaven, are impossibly thin, a delicate stone skin that should buckle under its own weight and the relentless push of the wind. The medieval solution was both brilliant and beautiful, the flying buttress. These stone ribs arching away from the walls are not just decorations, they are the cathedral's exoskeleton, actively channeling the crushing forces of the vaults down and out into the ground. It was a radical reimagining of architecture, turning solid walls into a framework of light and space. Modern engineers using sophisticated computer modeling, a process called finite element analysis, can now map the intricate dance of stresses within the stone. They confirm that the builders achieved a near-perfect balance, a distribution of forces so efficient it still defies easy improvement. Yet the stone framework is only half the mystery. Within it rests a treasure even more elusive, the stained glass, particularly the legendary Chartres blue. This cobalt hue, seen in windows like the Virgin Mary's robe, possesses a depth and luminosity that has never been successfully replicated. The exact medieval recipe, the specific blend of minerals, the temperature of the furnace, and the timing of the cooling process, all are lost. Modern glassmakers can create similar colors, but they lack the same radiant intensity and, crucially, the extraordinary durability. Chartres' original glass has survived centuries of weathering, wars, and pollution with a resilience modern chemistry struggles to match. So the cathedral stands as a dual testament, a masterclass in macro engineering with its skeletal stone frame, and a puzzle in micro engineering with its molecularly perfect glass. It is a complete system, a symphony where every element, from the grand arc of the buttress to the molecular structure of blue pigment, was tuned to a single purpose, creating a space that lifts the gaze and the spirit. This holistic genius asks us a profound question. Can we ever truly separate the art of a structure from its science, or were they, for these builders, one and the same? The luminous glass of Chartres demonstrates a mastery of material, but what happens when the very idea of the material is reimagined? In Florence, a gaping hole in the sky taunted the city for generations. The Cathedral of Santa Maria del Fiore stood unfinished, its crossing open to the elements, a monumental problem that had defeated every architect for over a century. The challenge was not just size but physics. To complete it required a dome wider than the Roman Pantheon, but the traditional method, building a massive wooden support scaffold called centering, was deemed impossible. The timber required did not exist in all of Tuscany, and the cost was unthinkable. The city held a competition, and the winner was a goldsmith and clockmaker named Filippo Brunelleschi, a man with no formal architectural training. His proposal seemed like madness. He vowed to build the dome without any centering at all. To his rivals, it was like promising to build a basket in mid-air. Brunelleschi's genius was a fusion of medieval craft and proto-scientific observation. He did not just design a dome, he engineered an entire new construction process. His solution was a double shell, a lighter inner dome supporting a sturdier outer one, with a hollow space between for workers to move and for the structure to breathe. But the true stroke of brilliance was in the bricklaying. He employed a herringbone pattern, laying the bricks in a series of inward-leaning, self-locking spirals. Each completed ring became a stable, horizontal base for the next, the dome literally building its own support as it grew skyward. It was a three-dimensional puzzle solved in real time, with mortar that set quickly to ensure each section was firm before the next began. For decades, the precise structural logic of these bricks was a mystery, a secret Brunelleschi guarded fiercely. Only with modern laser scanning have we fully mapped the ingenious geometry, a hidden order within the apparent chaos of the climb. Furthermore, to combat the dome's immense outward thrust, he secretly embedded chains of stone and iron within the ribs, like giant tension rings holding a barrel together, a primitive but profoundly effective use of tensile reinforcement centuries before the term was coined. Brunelleschi's dome is more than a landmark. It is a testament to one mind's defiant leap over the boundaries of accepted knowledge. It stands as a permanent rebuke to the idea of technological stagnation, proving that the medieval and Renaissance spirit was not one of blind tradition, but of relentless empirical problem-solving. He looked at an impossible void and did not see a limit. He saw a shape waiting to be born. Brunelleschi built his dome to touch the heavens, but the next structure was engineered for an entirely different purpose: to repel them. Perched atop a lonely hill in Syria, Krak des Chevaliers is not merely a castle. It is a stone manifesto on the art of survival. As a crusader fortress, it represents the absolute zenith of medieval military thinking, a machine built not for beauty but for relentless, calculated defense. Its defiance of modern engineering is not found in a single mysterious material or a staggering span, but in its terrifyingly efficient holistic design. Every slope, every wall, every corridor was a piece of a larger psychological and tactical puzzle, creating a system so resilient that a garrison of a few hundred could hold out against an army for years. The core principle was concentric defense, a series of nested walls and gates that forced any attacker into a sequence of fatal funnels. Imagine breaching the outer wall, only to find yourself trapped in a narrow killing ground, exposed to arrows and boiling liquids from the even higher inner wall above. This layered approach meant an invader had to fight for every inch, sacrificing scores of soldiers just to reach the next nearly identical challenge. The architecture itself was a weapon. Massive sloping walls called talus at the base were not just for grandeur, they caused siege projectiles to glance off harmlessly, a simple yet devastatingly effective form of medieval deflection. Stone projections called machicolations jutted out from the parapets, allowing defenders to drop stones or pour unpleasant substances directly down onto anyone at the base of the wall, a grim but effective innovation. Yet perhaps the most brilliant feature was one dedicated not to killing but to living. The castle contained an ingenious reservoir system, capturing and storing rainwater within its own walls. This meant that during a prolonged siege, while the attacking army outside might be struggling to find fresh water, the defenders inside could remain self-sufficient, turning time from an enemy into an ally. Modern military historians still study Krak des Chevaliers as a textbook example of defensive warfare, and engineers can analyze the strength of its limestone. But to replicate its genius is to replicate a mindset. It requires an intimate, almost symbiotic understanding of the terrain, turning a hill's natural advantages into an extension of the walls. It demands a psychological strategy built into the stone, designed to demoralize and exhaust an opponent at every turn. This fortress stands as a chilling reminder that medieval engineering was as much about understanding human weakness as it was about mastering material strength. It asks us, in a world of advanced weaponry, what have we forgotten about the pure, unyielding geometry of defense? From the psychology of defense, we move to a foundation of pure faith in physics. Salisbury Cathedral rises from a water meadow, a place where any modern engineer would hesitate to lay a garden shed. In the 13th century, with the water table just inches below the surface, the builders faced a seemingly insurmountable problem: how to anchor a mountain of stone in what was essentially a soft, wet sponge. Their solution was not to fight the water, but to float upon it. They dug a wide, shallow trench and filled it with a carefully layered raft of gravel and chalk, creating a massive, flexible platform that distributes the cathedral's immense weight evenly across the unstable ground. Think of it as a stone lily pad, engineered to settle as a single, unified mass rather than cracking into pieces. For over 800 years, this ingenious foundation has held, with the entire structure sinking only a few inches uniformly, a negligible amount given its staggering scale and the challenging site. This is not luck, it is a lost science of soil mechanics, an intuitive grasp of load distribution that would not be formally understood for centuries. The cathedral's defiance continues upward. Its towering spire, added a century after the main building, is the tallest in the United Kingdom and possesses a gentle, perceptible lean. Modern analysis reveals this is not a sign of failure, but a feature of its medieval flexibility. The original builders, perhaps anticipating future additions, designed the supporting pillars and arches with a slight inward tilt, creating a structural tension that acts like a clasped hand, resisting outward thrust. When the heavier spire was added, the entire system adjusted, settling into a new, stable equilibrium. The slight lean we see today is the signature of that centuries-old dialogue between stone and earth, a testament to a design philosophy that embraced movement rather than resisting it. Salisbury does not just stand on a meadow, it dances with it, a slow, imperceptible waltz measured in millimeters per century. It asks a humbling question of our own rigid concrete and steel. In our quest for absolute stability, have we forgotten the ancient wisdom of graceful adaptation? Florence holds another secret of resilience, one that bends with the river rather than the sky. The Pont Vecchio is more than a picturesque row of jewelers' shops. It is a masterclass in survival written in stone and water. Built in 1345, this bridge has withstood the fury of the Arno River for nearly 7 centuries, including catastrophic floods that have swept away modern, reinforced concrete bridges built downstream. Its defiance is a quiet, hydraulic genius. The medieval builders understood something fundamental that we often engineer out. A river is not a static enemy to be conquered, but a dynamic force to be negotiated. Their primary tool was the segmented arch, a flatter, wider curve than the classic Roman semicircle. This design allowed for a longer span with less upward thrust on the piers, those critical supports standing in the water. But the true brilliance lies in those piers themselves. Each one is shaped with massive, angular projections upstream called cutwaters. These are not decorative. During a flood, they act like the prow of a ship, cleanly slicing the onrushing water and diverting its immense force around the pier's sides, drastically reducing the direct pressure that could topple it. It is a principle of hydrodynamics applied with Stone Age tools and profound observation. Even more remarkable is the bridge's philosophy of sacrifice. Modern analysis suggests the Pont Vecchio embodies a concept known as planned weakness or sacrificial components. The design subtly allows certain non-critical elements, perhaps specific joints or spandrels, to fail under extreme stress. This controlled failure acts as a pressure valve, dissipating destructive energy and protecting the vital structural skeleton of the arches and piers. It is the architectural equivalent of a circuit breaker, sacrificing a small part to save the whole system. This intuitive grasp of systemic resilience is what allowed the bridge to endure not just floods, but the weight of centuries of shops and foot traffic, and even the retreating German army's decision to destroy every other bridge in Florence during the Second World War, leaving the Pont Vecchio mysteriously spared. It stands not as an inert monument, but as a living laboratory. Every stone in the water tells a story of adaptation, of building in conversation with a powerful and unpredictable natural world. While we now build for maximum strength at every point, the Pont Vecchio whispers an older, perhaps wiser truth, that true endurance sometimes requires knowing what to let go. The quiet negotiation of a river gives way to a conversation with the sky itself. In central Greece, colossal fingers of sandstone reach 1,000 feet into the air, worn smooth by time and wind. Upon their summits, as if grown from the rock, sit the Monasteries of Meteora. Established from the 14th century onward, these sanctuaries represent not an engineering conquest over nature, but a breathtaking act of integration. Their defiance is twofold: a staggering logistical puzzle of how they were built, and a profound geological puzzle of how they have survived. To reach these peaks, medieval monks did not carve roads or build grand staircases. They used a system of ropes, nets, and wooden winches, hoisting both building materials and themselves in a slow, vertical ascent that could take over half an hour. Each lift was a perilous exercise in trust and simple mechanics. The ropes replaced only, as the saying went, when the Lord let them break. This was construction as a literal leap of faith, where every stone and timber had to be flown to its destination. Once on the pinnacle, the real challenge began, anchoring a permanent structure to a living, breathing rock pillar. The builders employed techniques that modern extreme environment engineers and rock climbers still analyze. They sought out natural fissures and shelves, weaving the foundations of their buildings into the existing stone fabric. They used a form of gravity anchoring, ensuring the weight of the monastery transferred down along the strongest internal lines of the rock pillar, becoming an extension of the natural formation rather than a foreign weight perched upon it. This deep, empirical understanding of rock mechanics is why Meteora has endured. The region is seismically active, yet these monasteries have weathered centuries of tremors. The flexibility of their stone-on-stone construction, without rigid modern materials, allows them to sway and settle with the earth's movements. Furthermore, the monks displayed a keen awareness of erosion, building their structures set back from the very edges of the pillars to protect against crumbling. Their achievement is a masterclass in symbiotic design. They did not seek to flatten the mountain or dominate the cliff, but to become a part of it. In an age where we might solve this problem with helicopters, reinforced concrete, and deep drilling, Meteora poses a quiet, profound question. Have our powerful technologies made us less attentive students of the natural world? These monasteries remind us that the first principle of building in an extreme place is not to fight it, but to listen. Sound itself became a material to be shaped by stone. High within the dome of St. Paul's Cathedral in London, a visitor can lean close to its circular wall, whisper a secret, and have it travel with uncanny clarity all the way to someone standing directly opposite, over 100 feet away. This is the Whispering Gallery, a space where architecture bends acoustics to its will. While the cathedral was completed in the early 18th century, its design is a direct descendant of the medieval and Renaissance engineering tradition we have been exploring, a final flowering of that empirical, hands-on genius. The builders, led by Christopher Wren, were not just constructing a monument, they were crafting an experience. The phenomenon is no longer a complete mystery to us. We understand it as a perfect example of sound reflection. The specific, mathematically precise curvature of the dome's interior surface acts like a continuous acoustic mirror, channeling whispers along its circumference without the scattering and distortion that would occur in a less perfect shape. The density and smoothness of the stone further ensure the sound waves lose minimal energy on their journey, yet understanding the physics only deepens the achievement. To create this effect required an intuitive mastery of geometry and material, refined over generations of cathedral building, but executed here with a new level of intentional precision. Every stone in that vast curved wall had to be placed with an awareness of its role not only in holding up the dome, but in guiding a human breath. There were no microphones, no sound wave simulations, only careful observation, trial and error, and a profound belief that a sacred space should engage all the senses. This acoustic defiance is subtle but profound. It represents a leap from engineering for permanence to engineering for perception. The gallery manipulates a fundamental force of nature to create a moment of shared intimacy in a cavernous, awe-inspiring space, turning a simple whisper into a small miracle. It asks us to consider how much we lose when we design buildings solely with visual spreadsheets and structural calculations, forgetting that the true power of a space is often felt in the quietest, most unexpected conversations it allows. The silent acoustics of a stone dome give way to a different kind of quiet, the deep, resinous hush of an ancient forest preserved in architectural form. In the snowbound valleys of Norway, structures like the Borgund Stave church, built around the year 1180, stand as a defiant conversation with the cold. Their survival is a paradox crafted entirely from wood, the very material we would consider most vulnerable to the ravages of a northern climate, yet they have endured for over 8 centuries of relentless freeze and thaw, heavy snow, and driving damp. The secret is not in defying nature, but in designing with its very rhythms in mind. This is medieval engineering as a form of deep environmental intelligence. The entire structure is a complex wooden skeleton, a stave framework assembled without a single nail. Instead, master craftsmen used an array of intricate joints, like the massive sills and corner notches, that lock together with a precision that allows for minute-controlled movement. As the wood expands with summer humidity and contracts in the winter dry, the entire building breathes and shifts as a single, flexible organism. This inherent give is what prevents the catastrophic cracking that would destroy a more rigid, modern structure subjected to the same extreme temperature swings. The roof itself is a masterpiece of layered design, with multiple tiers that efficiently shed immense snow loads, preventing the crushing weight from accumulating. But the wood itself holds a deeper mystery. The black protective coating that gives these churches their distinctive appearance is not mere paint. It is a tar-based preservative, a recipe derived from slowly burning local pine in earth-covered pits. This ancient substance has done what many modern chemical treatments struggle to accomplish. It has repelled water, discouraged wood-boring insects, and inhibited fungal rot for hundreds of years. The exact formulation and application process, a product of generations of local knowledge, is now lost, a testament to a material science that was both sustainable and astonishingly effective. The Stave Church is a lesson in true biomimicry long before the term existed. It does not impose an alien form on the landscape. It emerges from it, using local materials in a way that acknowledges and adapts to local forces. Its endurance asks a pressing question of our own standardized, shipped-in construction methods. In our quest for universal solutions, have we forgotten how to listen to the specific whispers of a place, to build not just on the land, but in partnership with it? Its tilted silhouette is a global icon of unintended beauty. The Leaning Tower of Pisa is often celebrated as the world's most famous architectural mistake, but to label it a simple error is to miss its true, defiant genius. Its continued survival is not a story of luck, but a centuries-long demonstration of intuitive engineering under immense pressure. Construction began in 1173 on a foundation of soft, unstable subsoil, a mixture of clay, fine sand, and shells. By the time workers reached the third story, the structure had already begun its slow, graceful surrender to gravity. The medieval builders faced a crisis, abandon the project and accept colossal financial and reputational ruin, or find a way to build upward on a sinking base. They chose the latter, embarking on one of history's most daring acts of architectural improvisation. With no textbooks on soil mechanics, they relied on pure observation and craft. As they continued upward, they deliberately made the masonry on the sinking southern side slightly taller than on the northern side, attempting to correct the lean by adjusting the very geometry of each new level. This was not a precise calculation, but an intuitive, real-time response to a living, moving problem. They were not just building a tower, they were having a conversation with the ground beneath it, a dialogue written in stone and soil. For centuries, the tower leaned further, becoming both a marvel and a looming catastrophe. Then, in the 1990s, an international team of modern engineers faced the same fundamental challenge: how to stabilize the lean without causing collapse. Their sophisticated solution was, in essence, a refined echo of the medieval intuition. They carefully extracted small amounts of soil from under the northern, higher side of the foundation, allowing the tower to settle back toward the south in a controlled manner. It was a delicate millimeter-by-millimeter process, guided by lasers and computers, yet the core principle was astonishingly similar: gently persuade the ground to adjust. The tower's persistence teaches a profound lesson about dynamic soil-structure interaction, a concept formalized only in the modern era. Those 12th century masons, working with imperfect information and simple tools, were already engaging with this reality. They understood that their structure and its foundation were not separate entities, but parts of a single, responsive system. Their adaptive problem-solving in the face of the unknown is a skill as valuable as any software simulation today. The tower stands not as a monument to failure, but as a testament to human resilience and pragmatic ingenuity. It asks us, when our own plans begin to tilt, do we have the courage to adjust our course, to build not as we intended, but as the reality demands? Water is not just a barrier, it is a weapon of mass defense. In the rolling hills of Wales, Caerphilly Castle does not simply sit beside a lake, it commands an entire engineered sea. Built in the 13th century, its genius lies not in towering keeps or thick curtain walls, though it has those in abundance, but in its breathtaking ambition to reshape the landscape itself. This fortress is a masterwork of medieval hydrology, a sprawling network of dams, sluices, and artificial lakes that transformed the local valley into a shimmering, impassable shield. The scale is staggering, even by modern standards. Its concentric moats are not mere ditches, but vast, interconnected bodies of water covering many acres, fed by a complex system that managed inflow and outflow with the precision of a modern reservoir. To create this, medieval engineers had to solve problems we associate with civil engineering today. They built massive earthen dams strong enough to hold back millions of gallons of water, and designed clever sluice gates to control water levels, preventing overflow that could weaken the earthworks or, conversely, a drop that could expose a muddy approach for attackers. This was environmental modification as a strategic doctrine. The castle did not just occupy a site, it became the heart of a manufactured ecosystem, an island fortress whose first and greatest wall was a reflective sheet of water. What is truly humbling is the longevity of this system. While modern concrete dams and levees require constant monitoring and repair, Caerphilly's medieval earthworks and stone-reinforced dams have managed water levels with minimal intervention for over 700 years. They have endured centuries of Welsh rain, seasonal floods, and the slow creep of vegetation, maintaining their structural integrity through a combination of robust design and an intuitive understanding of local hydrology. The builders used materials at hand, clay and earth and stone, and shaped them in harmony with the land's natural drainage. This castle challenges our perception of medieval capability. It proves that their military vision extended far beyond the battlements, into the realm of large-scale environmental engineering. They thought in terms of watersheds and water tables, using liquid geography as a permanent, sustainable defense. In an age of rising seas and crumbling infrastructure, Caerphilly poses a quiet, profound question. When we build our own defenses against nature, do we seek to conquer it, or could we learn again to collaborate with its fundamental forces? While water could shield a fortress, stone was tasked with defending an empire. The Theodosian walls of Constantinople were not a single barrier but an entire ecosystem of defense, a layered labyrinth that protected the heart of the Byzantine world for over 800 years. Built in the 5th century, this was not just a wall, it was a city's immune system, a 12-mile-long stone skin designed to identify, trap, and neutralize any threat. Its legendary status is not hyperbole. It was a system so effective it was never truly breached by force until the advent of gunpowder artillery in 1453. The secret to its longevity was not brute thickness but brilliant, adaptable complexity. Imagine approaching as an attacker. First, you faced a wide, deep moat that could be flooded, a watery no-man's land. Beyond that rose a low outer wall, manned by archers and infantry. If you somehow scaled that, you would drop into a deadly killing zone called the Peribolos, a broad terrace completely exposed to the murderous fire from the massive inner wall looming above you. This inner wall stood 40 feet high and was studded with 96 towers, each spaced to provide overlapping fields of archery and catapult fire. Every element was a piece of a larger tactical puzzle, forcing an enemy to solve one lethal problem only to be confronted by another, worse one. But the true engineering defiance is in the material itself, the mortar that binds these ancient stones. Modern analysis reveals it was no simple lime mixture. The builders likely incorporated crushed brick and ceramic fragments, a technique known as pozzolanic cement that the Romans used, creating a concrete-like binder that is incredibly durable and even gains strength over time as it reacts with moisture. This mortar gave the walls a flexible, monolithic quality, allowing them to absorb and dissipate the energy of earthquakes and siege engine impacts rather than shattering. The walls were designed to sway and settle, not to remain rigid and brittle. This ancient understanding of composite materials and energy dissipation is now a cornerstone of modern engineering, particularly in designing structures to withstand seismic events or even blast forces. The Theodosians' walls teach a timeless lesson in holistic resilience. They prove that the strongest defense is not a single, impenetrable barrier, but a system of integrated, redundant layers, each with a specific role, all working in concert. It is a philosophy that moves beyond mere strength toward intelligent, adaptive endurance. While we now use polymers and steel rebar, the principle remains the same. To build something that can endure, you must first understand all the ways it might be broken. Granada's Alhambra is a fortress that conquered the climate. While other castles relied on thick walls for defense, this 13th century Nasrid palace complex waged a subtler, more enduring war against the harsh Spanish sun. Its true genius lies not in repelling armies, but in mastering the two most precious resources in an arid land, water and air. To walk its courtyards is to step inside a living machine of exquisite elegance, where every element serves a dual purpose of beauty and profound environmental engineering. The system begins high in the Sierra Nevada mountains, where snowmelt is captured and channeled through a network of ancient acequias, or irrigation canals. These channels are not crude ditches, but carefully graded waterways, their slopes calculated with such precision that water flows at a constant, gentle pace all the way to the palace gates, powered by gravity alone. The gradient is so exact that modern engineers, using laser levels and digital theodolites, have measured it and found it nearly perfect, a feat achieved with nothing more than sighting poles and generations of accumulated observation. Once inside the Alhambra, the water performs a ballet of cooling. It cascades into serene, reflecting pools in the Court of the Myrtles, where the large surface area allows for evaporative cooling. It murmurs through narrow rills lining the walkways of the Generalife Gardens, chilling the stone pathways. It erupts in delicate fountains whose sound masks the noise of the city below while filling the air with moisture. This entire hydraulic network creates a self-sustaining microclimate, dropping the temperature by several degrees within the palace walls, a natural form of air conditioning devised 7 centuries before the invention of the mechanical compressor. The coolness is held and amplified by the architecture itself. Look upward in the Hall of the Abencerrage or the Hall of the Kings, and you will find the ceiling dissolved into a breathtaking cascade of stone, the muqarnas. These honeycomb or stalactite vaults are often admired as pure ornament, but they are equally a feat of structural and environmental logic. Their complex geometric patterning is a 3-dimensional puzzle of interlocking niches, distributing weight across a broad area with minimal need for massive supporting walls. This creates large, open, column-free spaces ideal for air circulation. Furthermore, the countless concave surfaces of the muqarnas help to diffuse and reflect light softly throughout the room, reducing glare and heat gain from the sun, while also potentially baffling sound to enhance acoustics. The Alhambra stands as a holistic manifesto. Here, art is not applied to engineering, science is not separate from aesthetics. The cooling breeze, the play of light on water, the intricate shadow cast by a stone honeycomb, all are part of a single, integrated system for sustainable living. It represents a philosophy where human comfort and artistic splendor are achieved not by dominating the environment, but by understanding its flows and rhythms so deeply that the building itself becomes a serene and responsive extension of the natural world. Deep within the soft volcanic rock of Cappadocia lies a city that turned the very earth into a sanctuary. Derinkuyu is not a collection of buildings, but a sculpture of emptiness, an entire inverted metropolis carved by hand beginning in the 7th century. Its scale is the first shock, descending nearly 300 feet through at least 18 labyrinthine levels, with space for perhaps 20,000 people along with their livestock, food stores, and places of worship. To stand at its entrance is to confront a question that defies modern urban logic. How do you keep a city of that size and depth alive? The answer is a masterpiece of passive engineering, a breathing stone lung. The builders carved over 50 slender ventilation shafts, some stretching from the deepest chambers all the way to the surface. These were not random holes, but carefully placed chimneys that harnessed the natural principle of convection. Cooler, fresh air would be drawn down into the lower levels, while warmer, stale air would rise and escape through other shafts, creating a constant, life-sustaining circulation without a single moving part. It was natural air conditioning and life support, engineered with nothing but an intuitive grasp of physics and a deep understanding of the rock's properties. But a city that breathes must also be able to seal its lungs in an instant. The defensive genius of Derinkuyu is embodied in its massive, circular stone doors. These are not gates in a conventional sense, but immense millstone-like slabs of rock perfectly balanced on a central pivot. In times of danger, a few people could roll these doors from within, completely blocking the narrow connecting tunnels. Each door featured a small, central hole, not for attack, but for a last line of communication or perhaps to challenge an intruder. This design created a series of defensible compartments, allowing the community to retreat deeper and seal each level behind them, turning the entire city into a sequence of impassable vaults. The structural stability of this hand-carved world is its most silent defiance. The soft, tough rock might seem fragile, but the builders understood its compressive strength. They carved rooms with rounded corners and arched ceilings, shapes that naturally distribute weight and prevent stress points, mimicking the stability of natural caves. They left strategic columns of untouched rock to act as central supports, and ensured that upper levels were carved with thicker ceilings to bear the load of those above. This intuitive rock mechanics is why Derinkuyu has survived over 1,000 years of seismic activity in a tectonically active region, while modern underground constructions require extensive reinforcement. This was not architecture imposed upon the landscape, but a dialogue with it, a communal project where safety was woven into the very fabric of the stone. It represents sustainable, disaster-resilient living on a monumental scale, a lesson carved in darkness on how to find profound security, not by building higher, but by understanding the ground beneath our feet more deeply than we ever thought possible. A city carved from rock demonstrates survival through retreat, but true naval power demanded the opposite, a bold advance into the very element that threatened it. On the south coast of England, the restless tides of the Solent presented a constant, grinding problem for the Tudor navy. A wooden warship was a living thing, its hull besieged by worms, barnacles, and rot, needing constant care. Hauling a massive vessel onto shore was a slow, destructive ordeal, leaving it vulnerable. The solution, conceived in the reign of King Henry VIII and built at Portsmouth in the 1500s, was an act of sheer hydraulic audacity, a structured dry dock. This was not merely a hole in the ground by the water, it was a sophisticated machine for defying the sea on a daily basis. Its genius was a system to command the tides. At its heart was a massive, watertight gate called a caisson, a floating box of timber that could be maneuvered to seal the dock's entrance. Coupled with a network of sluices and channels, this allowed engineers to control the water level with a precision that feels modern. When a ship needed repair, they would float it in at high tide, close the caisson gate, and then open the sluices to let the outgoing tide drain the dock, leaving the vessel sitting high and dry on a prepared bed. The reverse process would refloat it. The concept is fundamental to every naval base in the world today, but its first successful execution here was a medieval triumph. The defiance lies in the brutal physics of the site. Building anything permanent in the tidal zone is a battle against colossal, cyclic forces. The dock's timber walls had to withstand the immense, fluctuating pressure of water on one side and the crushing weight of earth on the other, all while remaining perfectly sealed. This required a masterful understanding of hydrostatics, the behavior of fluids at rest, and joinery so precise that the massive planks would swell tight against each other when wet, creating a seal that actually improved with use. There were no rubber gaskets, no industrial pumps, only wood, iron, and a profound comprehension of the sea's rhythm. This facility was not just a technical wonder, it was a direct instrument of geopolitical power. By dramatically extending the operational life and readiness of the royal warships, the dry dock transformed naval logistics. It meant England could maintain a standing fleet capable of rapid deployment, a strategic advantage that shaped the destiny of a nation. It stands as a powerful reminder that medieval engineering was often at its most brilliant not in the service of faith or defense alone, but in the pragmatic, unsung infrastructure that turned a kingdom's ambition into tangible, enduring strength. Stone becomes lace, and gravity seems a forgotten suggestion. High above the choir of King's College Chapel in Cambridge, the world's largest fan vault stretches its delicate stone tracery, a frozen explosion of geometry that has captivated and confounded observers for 500 years. To stand beneath it is to feel a profound disorientation, the solidity of the material betrayed by its apparent weightlessness. This is not a ceiling, it is a canopy of stone flowers, each petal a precisely carved rib springing from the wall and blooming overhead in a symmetrical cascade. The perpendicular Gothic style reaches its breathtaking zenith here, not as mere decoration, but as a structural argument written in limestone. The defiance is in the illusion. The vault appears to hang from above, a suspended web, yet every ounce of its immense weight is actively channeled downward through a hidden intelligence of force. Each fan is a masterful distribution network, a concave semi-cone of ribs that gather the load from the vast ceiling and funnel it efficiently down slender stone shafts to the walls and ultimately to the mighty buttresses outside. It is gravity made visible, turned into a pattern of exquisite beauty. The true marvel, however, lies in the hands that built it. This entire stone tapestry was assembled in the early 16th century, an era without computer modeling, without powered tools, without standardized measurements. The masons worked from full-scale templates painstakingly drawn on tracing floors, large rooms where the intricate curves of every rib and panel were chalked out at life size. Each block of stone was then individually cut by hand to match these unique templates, a three-dimensional puzzle comprising thousands of non-interchangeable parts. The precision required was staggering, a margin of error measured in millimeters over a span of hundreds of feet. A single miscut stone could throw off the alignment of an entire bay, compromising the delicate balance of thrust and counter-thrust. This was not construction, it was high-stakes sculpture at a monumental scale, relying on a craftsman's intuitive grasp of geometry and volume, knowledge passed down through generations of master builders. Today, we could digitally scan and robotically carve each piece with flawless accuracy, but to do so with the same manual tools, the same empirical understanding, and achieve the same cohesive, living result would be a challenge of almost unimaginable skill. The vault is a testament to a different kind of intelligence, one where the mind, the eye, and the hand were in perfect, trained harmony. King's College Chapel ultimately dissolves the line we often draw between engineering and art. In this space, structural necessity did not limit beauty, it defined it. Every rib has a job to do, every curve is a response to a physical law, yet together they create an atmosphere of transcendent lightness. The vault does not hide its mechanics, it celebrates them, turning the sober mathematics of load-bearing into a visual symphony. This is the culminating dream of Gothic ambition, to make the sacred visible not through painting or statue alone, but through the very fabric of the building itself. The stone seems to breathe, to reach, to ascend. It challenges our modern compartmentalization, where an architect's vision is handed to an engineer to make possible. Here, the visionary and the pragmatist were one and the same, guided by a tradition that understood strength could be graceful, and that the most profound stability might look like it is floating on air. What does this tell us about the goals of building? Perhaps true mastery is not about making heavy materials seem strong, but about revealing the hidden lightness within their strength. While stone vaults achieve a celestial lightness, wood can be engineered to shelter an entire kingdom beneath a single, mighty span. Westminster Hall's roof is not a covering, it is a forest-turned architecture, a 14th-century timber titan that has sheltered the heart of English history for over 600 years. To stand beneath it is an experience of pure awe, your gaze drawn up 72 feet to a canopy of ancient oak that stretches clear for more than 68 feet in width, with not a single column or pillar interrupting the vast floor below. This was the grandest room in medieval England, a space built for royal ceremonies, feasts, and courts of law, and its roof needed to be a statement of both power and profound technical mastery. The solution was the Hammerbeam, a design so ingenious it feels like a carpenter's secret spell against gravity. At first glance, the roof seems to float, a complex lattice of beams and arches. But its secret lies in a brilliant redistribution of force. Instead of relying on long, single beams that would sag under their own weight over such a span, the medieval carpenters used a series of shorter, horizontal hammerbeams that project inward from the walls. From the ends of these beams, massive arched braces swoop upward and inward, supporting a second tier of hammerbeams and then another, creating a cascading, self-supporting truss. Each piece pushes and pulls against the others, channeling the immense weight of the roof not downward into the center of the room, but outward and down along the massive stone walls. It is a lesson in turning compression and tension into a stable, wooden embrace. The material itself was chosen with a wisdom we are only now relearning. The oaks were not just cut, they were selected from specific forests, felled in a particular season, and then seasoned for years, allowing the wood to stabilize and reach its peak strength naturally. The jointing is where the true magic resides. Each of the thousands of connections uses complex mortise and tenon joints, secured with wooden pegs, a system that allows for controlled movement as the wood breathes with centuries of changing humidity. This flexibility is its resilience. It has allowed the roof to survive the Great Fire of London in 1666, which raged around it, and the incendiary bombs of the 20th century, settling and adjusting where a rigid, modern structure might have shattered. Today, timber engineers study this roof with a sense of reverence. Modern glued laminated beams and cross-laminated timber are technological marvels, but they seek to achieve what this medieval roof demonstrates naturally: an extraordinary strength-to-weight ratio and a longevity measured in half millennia. The carpenters of Westminster Hall possessed a deep, material-specific wisdom. They did not see wood as a substitute for stone, but as a living partner with its own unique language of strength. They built in concert with its grain, its natural properties, and its future behavior, crafting a shelter that is as much an ecosystem as it is an engineering feat. It asks us a quiet question in an age of synthetic composites. In our rush to invent new materials, have we forgotten how to fully converse with the oldest ones we have? The silent, enduring strength of timber points our attention upward, to a different kind of alignment written not in wood, but in light itself. Walk into any great medieval cathedral in Europe, and you will likely be standing on a living compass. From Notre Dame de Paris to countless smaller parish churches, these structures share a profound directional precision, their altars facing almost perfectly east toward the rising sun. This is not a vague tradition, but an architectural fact achieved on a continental scale, and it presents a quiet, magnificent defiance. These buildings were oriented with astonishing accuracy centuries before the magnetic compass became a standard tool for European builders. How did they manage such consistent, large-scale alignment across thousands of miles without our modern instruments? The answer lies in a forgotten dialogue between heaven and earth. Builders were master observers of the sky, using the sun and stars as their primary guides. A common method involved marking the shadow of a stake at sunrise and sunset on the day of the church's patron saint, then bisecting the angle to find true east. This required not only clear skies and patience, but a deep, communal understanding of the solar calendar and its connection to sacred time. It was astronomy applied with spiritual intent, turning the very act of foundation into a ritual that anchored the building to the cosmos. The precision achieved is humbling. Studies of cathedral alignments show deviations often measured in mere fractions of a degree, a level of accuracy that rivals modern surveys for such large projects. This points to a sophisticated, shared knowledge system passed among guilds of masons, a living science of celestial navigation and land surveying that wove spiritual symbolism into practical necessity. The eastward orientation was rich with meaning, symbolizing the resurrection and the dawn of salvation, but the means to achieve it were rigorously empirical. This alignment did more than point a building, it shaped the landscape. Roads, town squares, and even property lines would often radiate from or conform to the church's sacred axis, embedding this celestial order into the daily fabric of medieval life. The cathedral was not just a place of worship, it was the central reference point for an entire community's sense of direction, both physical and spiritual. In our world of satellite positioning and digital mapping, this achievement asks us to reconsider what we mean by navigation. For these builders, to find true east was to connect their work to a universal order, to build in harmony with the fundamental rhythms of light and time. It is a reminder that the greatest precision often begins not with a tool, but with a profound act of observation and a desire to align human creation with something timeless. A perfect castle was never finished. On the windswept coast of Wales, the grey limestone walls of Beaumaris Castle rise from a flat, marshy plain, a geometric dream frozen in stone. Begun in 1295 under the command of King Edward I, this fortress represents the absolute pinnacle of medieval military engineering, a machine of war designed with a cold, mathematical purity. Its defiance lies not in surviving epic sieges, for it never saw major combat, but in its existence as a flawless blueprint made real, a theoretical ideal executed on a staggering scale. Beaumaris is the ultimate concentric castle, a form so refined it feels like a diagram sprung to life. Picture two complete castles, one nestled inside the other. A wide, tidal moat fed by the sea surrounds a low outer wall studded with 16 towers and 2 fortified gatehouses. Behind that wall lies the outer ward, a broad killing ground. Then, rising higher and thicker, stands the majestic inner wall with its 6 massive towers and 2 great gatehouses, forming an impregnable inner stronghold. The genius is in the sightlines. Every inch of the outer wall, every approach across the moat, is covered by arrows and missiles from the inner wall. There are no blind spots, no sheltered angles for an attacker. An invading force would have to breach 2 separate, complete fortifications while under constant, murderous fire from above, a task of almost unimaginable cost. Modern military architects and historians study Beaumaris with a sense of awe, for it is the logical conclusion of centuries of defensive evolution. It is not an adaptation to a hilltop or a piecemeal expansion, but a complete system conceived and executed from the ground up as a single, optimized unit. The resources marshaled for this project were colossal, requiring the labor of thousands and a budget that nearly bankrupted the English crown. This scale of pre-planned, systematic construction, where every element serves a calculated role in a grand design, is a mindset we deeply associate with modern civil engineering and architectural firms. The builders of Beaumaris were not just stacking stone, they were implementing a master theory of defense, thinking in terms of fields of fire, layered redundancy, and logistical control. That they could translate this complex theory into reality, coordinating such a vast workforce and supply chain in a remote location, is a testament to a highly developed medieval capacity for project management. The castle's unfinished state, a result of exhausted funds, only adds to its poignant legacy. We see the perfect skeleton, the full vision, but not the final flesh. It stands as a frozen moment of peak understanding, a monument to the moment when medieval military engineering reached its purest, most formidable expression. It asks us to consider the power of the perfect idea and what it costs to bring such an idea, however incompletely, into the world. Sound itself can be carved from stone with the same precision as an arch. The choir of Cologne Cathedral, a space consecrated in 1322 but following a plan laid out in the 13th century, is not just a passage for voices, it is a grand acoustic instrument meticulously tuned over generations. Its soaring Gothic vaults, rising to a precise height of 143 feet, were shaped by a goal that transcends structural integrity to create the perfect resonant chamber for the human voice in prayer. Every surface, from the angle of the stone walls to the specific density of the limestone itself, was selected and shaped to cradle sound, to extend a single note or a unified chant into a lingering, ethereal cloud that fills the entire space. The targeted acoustic property here is a long reverberation time, often exceeding 8 seconds, a duration that would muddy modern speech but which transforms plain song into a transcendent, enveloping experience. This was engineering for the soul, a calculated sensory architecture. Achieving this without a single digital simulation or even a reliable way to record and analyze sound waves represents one of the most subtle forms of medieval genius. It could only have been the result of an empirical, deeply observant process refined over decades, even centuries, of builders and musicians working in concert. A master mason might adjust the curvature of a vault ever so slightly based on the reports of singers, or select a stone from a particular quarry because it seemed to ring truer when struck. Knowledge was passed not through equations but through lived experience and careful listening, a slow accumulation of acoustic intuition written into the very bones of the building. This intentional design of atmosphere reveals a profound truth about medieval engineering. Its ultimate purpose was often to create an immersive environment, a total experience that engaged the body, the eye, and the ear in the act of worship. The structure was not an end but a vessel, a means to shape human perception and elevate a communal moment into something timeless. The choir at Cologne stands as a silent testament to this holistic vision, proving that the greatest buildings are not merely seen but deeply, resonantly felt. The soaring ambition of a stone spire is a silent battle against the wind. Strasbourg Cathedral's needle, completed in 1439, pierced the sky as the tallest structure humans had ever built, a title it held for over 2 centuries. Its defiance is not in its height alone, but in its impossible slenderness, a delicate stone filament that has withstood the gales of the Rhine Valley for nearly 600 years. The medieval solution to this lateral threat was both radical and prescient. They stitched the stone together with iron. Long before the steel skeletons of modern towers, the builders of Strasbourg embedded a hidden armature of iron rods and chains within the masonry, a tensile web tying the fragile spire together from the inside. This was a primitive but brilliant understanding of a core modern principle, using metal in tension to resist the bending and shearing forces of the wind, creating a composite structure where stone handled compression and iron managed the pull. To envision teams of workers hauling these heavy metal components up a precarious wooden scaffold, then carefully positioning them within the rising stonework, is to witness a breathtaking act of faith in an unproven idea. They were engineering in real time, responding to the invisible push of the air with a reinforcement strategy that foreshadowed the rebar in our concrete and the moment frames in our skyscrapers. Constructing this stone needle without material testing, without wind tunnel simulations, and with only rope and courage for safety, represents one of history's greatest calculated gambles. It pushed the very limits of the possible, transforming a cathedral's silhouette into a daring experiment that asked a monumental question: how do you make stone fly? The answer, woven in iron, whispers that the medieval mind was already dreaming of the skeletal cities to come. While a spire fights the wind, a wall can be designed to converse with the sun. The Romanesque bulk of Durham Cathedral, begun in 1093, feels like a fortress of faith, its walls so thick they seem to speak only of permanence and defense. Yet within that formidable stone mass lies a quieter, more brilliant intelligence, a mastery of climate crafted centuries before words like sustainability entered our vocabulary. These walls do not merely enclose space, they actively manage it, functioning as a colossal thermal battery for the soul. The principle is one of profound simplicity and deep observation. The vast quantity of limestone absorbs warmth from sunlight and from the body heat of congregants during the day, slowly storing that energy within its dense core. Then, as the cool English night descends, the stone gently releases that stored warmth, mitigating the chill and maintaining a remarkably stable interior temperature. This passive thermal mass buffers the cathedral against the extremes of the external world, creating a haven of constancy in a changeable climate. But the stone is only part of the environmental system. The builders positioned the cathedral with careful consideration, and its window design facilitates a natural ventilation strategy. Strategically placed openings, including the clever use of the triforium gallery, allow for cross-ventilation, drawing fresh air through the nave and flushing out stale air without a single moving part. This is bioclimatic architecture in its purest form, a total design philosophy that uses the building's own form, materials, and orientation to achieve human comfort. It required no fossil fuels, no complex machinery, only a deep, intuitive reading of the local environment and a patient understanding of material properties. The result was a sacred space that remained usable and spiritually focused throughout the year, from the depth of winter to the height of summer. Today, as modern architects and engineers strive to create net-zero energy buildings, they are returning to these ancient principles with new reverence. Concepts like thermal lag, passive solar gain, and stack ventilation are now analyzed with sophisticated software, but they were being practiced empirically at Durham nearly 1,000 years ago. The cathedral stands as a monumental lesson in efficiency, not of machines but of mindset. It challenges our reliance on active, energy-intensive systems to solve problems that a thoughtful design, in harmony with its place, can solve passively for centuries. It asks us a quiet, urgent question in our race toward a sustainable future. Are we inventing new solutions, or are we finally learning to listen to the wisdom already embedded in the oldest stones among us? Even the most intentional design can give birth to an accidental marvel. In the heart of Bologna, two brick giants have been locked in a silent, sloping duel for over 800 years. The Asinelli Tower and its shorter neighbor, the Garaisenda, are medieval skyscrapers born from a contest of pride between rival families in the 12th century, each constructing a tower to proclaim their wealth and power. Their continued defiance is not of invasion, but of physics itself. The taller Asinelli Tower leans noticeably, about 1.3 degrees, a persistent tilt that has withstood fires, wars, and the relentless passage of time, a testament to the robust, if imperfect, craftsmanship of their brick and mortar construction. But the true wonder of these towers is not just that they stand, but how they play tricks on the eye. From specific vantage points in the city's narrow streets, their paired lean and close proximity create a captivating optical illusion. They can appear to bend toward or away from each other in ways that defy straightforward perspective, an unintended visual poetry that the medieval builders could never have mathematically planned. This accidental artistry reminds us that the most enduring structures often hold secrets their creators never knew they were building into the stone. Yet the intentional achievement here is staggering in its own right. Erecting structures of such immense height, with the Asinelli reaching nearly 330 feet, in a dense urban center was an act of breathtaking audacity. Using only brick, mortar, and human labor, these families solved problems that modern city planners still grapple with: how to pack tremendous vertical load into an extremely small footprint. The foundations had to anchor a colossal weight onto the limited patch of earth each family owned, requiring a deep, intuitive understanding of soil-bearing capacity and load distribution. The construction itself, rising story by story from the crowded city floor, was a logistical puzzle of hoisting materials and workers skyward within a tight, bustling environment. In their rivalry, they pioneered a form of high-density urban engineering, creating landmarks that defined the city's silhouette and demonstrated a vertical ambition centuries ahead of its time. Their legacy is a double lesson: in the boldness of human ambition to build upward, and in the beautiful, unexpected consequences that emerge when those ambitions are set in stone, slightly askew, and left to converse with the centuries. Even a labyrinth on the floor can be a map of the heavens. The great circular maze laid into the stone of Chartres Cathedral, a path for pilgrims to walk in contemplation, holds a final, whispering layer of mystery beyond its spiritual function. Some researchers looking past its obvious geometry have proposed a startling idea that its intricate 11-circuit pattern may not be random, but a subtle reflection of lunar cycles. The suggestion is that the labyrinth could serve as a kind of calendar or astronomical diagram, encoding the complex rhythm of the moon's phases within its sacred geometry. This possibility connects directly back to the cathedral's most famous treasure, the ethereal Chartres blue of its stained glass. During the equinoxes, when day and night are of equal length, specific shafts of sunlight are known to pierce the cathedral's interior with dramatic precision, illuminating particular windows and architectural features. It is theorized that the unique properties of this blue glass, its molecular composition designed to capture and transform light, were not merely for beauty, but were calibrated to interact with these annual solar events. The glass would not just be illuminated, it would come alive, its color depth and luminosity shifting in the precise golden light of the equinox sun, turning the entire space into a cosmic clock. Whether these alignments were a deliberate act of the master builders or a profound, emergent property of their holistic design remains a subject of scholarly debate. Yet the very possibility speaks to a medieval worldview that seems almost alien in its unity. For these creators, there was no clean division between the engineer, the artist, and the astronomer. To build a house for the divine was to engage with the fundamental order of creation itself, an order expressed in mathematics, in light, in stone, and in the cycles of celestial bodies. The cathedral was not just a shelter for prayer, it was a three-dimensional encyclopedia, a machine for generating awe that also quietly recorded the movements of the moon and sun. This integrated philosophy represents perhaps the most profound defiance of all, a challenge to our modern, compartmentalized way of knowing. We separate physics from art, engineering from spirituality, architecture from cosmology. Chartres suggests that these builders saw them as threads in a single, magnificent tapestry. The structure's purpose was layered, holding a symbolic, even cosmological meaning within its very bones. This asks us to reconsider what we build for. Is a structure's purpose only its immediate practical function, or can it also be a vessel for a deeper kind of knowledge, a silent teacher woven into the play of light and shadow across stone? The final structure is not made of stone but of time and collective will. Our 25th marvel is the medieval cathedral building campaign itself, a project that could span 300 years and outlive every single person who first broke ground. Think of Canterbury Cathedral or the epic undertaking at Cologne, where work began in the 13th century and the final stone was not laid until the 19th. This is not the story of a single genius, but of a chain of hundreds of master builders, thousands of masons and carpenters, and dozens of generations who all contributed to a single, evolving vision. Their defiance is not against gravity, but against the very nature of human transience. How do you maintain the integrity of a staggeringly complex design across centuries, through wars, plagues, and shifting architectural tastes, without the permanent records we take for granted today? The answer lies in a living system of knowledge, a distributed consciousness etched into wood, plaster, and memory. The master plan did not live on a single sheet of parchment. It existed on full-scale tracing floors, large rooms where the intricate outlines of windows, arches, and vault ribs were scratched into plaster or painted on the floor. Each new master mason would consult these giant drawings, and craftsmen would use them as templates to shape their stones. Three-dimensional models, often exquisitely detailed in wood, served as the shared reference for the entire worksite, communicating proportions and relationships in a way two-dimensional plans could not. Most critically, knowledge flowed through an unbroken oral and practical tradition, from experienced journeyman to apprentice, a continuous conversation in stone and mortar that carried the project's DNA forward. This system was remarkably resilient. It allowed for adaptation, as a new master might subtly refine the design of a spire based on lessons learned from a collapse elsewhere, improving upon the original concept. The project could evolve organically, incorporating new Gothic innovations decades after the foundation was laid, because the system was built for continuity, not rigid preservation. This represents a form of institutional memory and collaborative project management on a scale that modern megaprojects, with their brittle dependence on digital files and short-term funding cycles, can still learn from. It was a civilization-scale endeavor funded by entire communities over lifetimes, a testament to a shared purpose that transcended any individual lifespan. The true cathedral was not just the finished building, but the centuries-long act of faith that built it, a collective promise to the future written one stone and one generation at a time. These patterns are not a random collection of clever tricks, but a coherent language of resilience. When we step back from the individual marvels, a unified philosophy of building comes into focus, one that speaks in a dialect our modern world has largely forgotten. The first and most fundamental pattern is a profound intimacy with material. Medieval builders did not see stone, wood, or lime as generic commodities to be forced into a design. They were students of their local environment, selecting and shaping materials based on a deep, empirical understanding of their unique behaviors. They used oak not just because it was strong, but because they knew how its grain would move with the seasons, crafting joints that allowed for that movement as a feature, not a flaw. They mixed mortars with local additives like crushed brick or volcanic ash, creating self-healing chemistries that responded to their specific climate. This was not engineering with off-the-shelf components. It was a conversation with the very substance of a place. The material was the teacher, and the builder was a lifelong apprentice, learning its strengths, its weaknesses, and its secret harmonies. This material intimacy naturally expanded into a second pattern, holistic integration. For these master builders, a structure was never just a roof and four walls. It was a complete, living system. A cathedral was an acoustic instrument, a solar calendar, and a thermal battery. A castle was a hydrological network, a psychological weapon, and a self-sufficient community. A bridge was a hydrodynamic sculpture and a planned sacrificial component. There was no separation between architecture, engineering, and environmental science, because the goal was to create a total environment that served multiple, interconnected purposes. The building was not an object placed on the land. It was an organ grown from it, processing light, sound, water, and air to sustain human life and aspiration. This system's thinking is what gave these places their enduring vitality. They were not static monuments, but dynamic participants in their ecosystems. How was such profound integration achieved without our scientific theories? The third pattern provides the answer: adaptive empiricism. This was a knowledge system built not from textbooks, but from the ground up through relentless observation, courageous experimentation, and learning from failure. It was engineering as a collective, ongoing experiment. When a tower began to lean, they observed how it settled and adjusted their next courses in real time. When a vault collapsed, they studied the rubble to understand the fault lines of force, then designed a new rib pattern to compensate. Knowledge was stored not in libraries alone, but in the scars on a master mason's hands, in the full-scale drawings on a tracing floor, and in the oral traditions passed from elder to apprentice on the worksite. This was a pragmatic, iterative wisdom, always being tested against the unforgiving reality of gravity and weather. All of this was guided by a fourth, and perhaps most alien, pattern to our modern sensibility, a long-term perspective. These projects were conceived with timescales that humble our quarterly reports and political cycles. They built for centuries, accepting that the true finished form might only be seen by the grandchildren of the original builders. This patience was not born from inefficiency, but from a different understanding of value and legacy. It allowed for adaptation across generations, for funding models that spanned lifetimes, and for a quality of craftsmanship that could only be achieved when the deadline was not a date on a calendar, but a standard of perfection that would echo through time. This perspective freed them to think in terms of permanence, resilience, and deep integration, rather than quick completion and immediate return. Together, these four patterns reveal a different paradigm entirely. Medieval engineering was context-sensitive, rooted in the specifics of place and material. It was multifunctional, weaving together structural, environmental, and symbolic purposes into a single fabric. It was empirical and adaptive, learning by doing and improving through shared experience. And it was profoundly patient, building for a future it would never see. In our pursuit of universal solutions, standardized materials, and rapid deployment, we have gained incredible speed and scale. But these 25 structures stand as quiet, persistent questions, asking us what we may have sacrificed in that trade. They challenge us to consider whether our modern methods, for all their power, have lost something essential, that deep, conversational partnership with the world we are trying to build upon. From the whispering galleries of St. Paul's to the hydraulic genius of the Alhambra, our journey through these 25 structures reveals a startling truth. The medieval world was not a dark age of engineering, but a brilliant age of applied wisdom. This was not a time of ignorance waiting for enlightenment, but a period of deep, observational intelligence, where solutions were carved from the very constraints that defined the era. These builders, with their hand tools and profound faith, solved intricate puzzles of physics, material science, and environmental design that we, with all our advanced technology, still find mysterious and deeply inspiring. They achieved acoustic perfection without microphones, climate control without compressors, and foundations on swamps without geotechnical surveys. Their work stands not as a primitive precursor to our own, but as a parallel achievement, a testament to a different kind of genius rooted in intimacy with the natural world. This legacy challenges us directly. It asks us to look beyond our computer models and standardized materials, to reconsider the immense value of local knowledge, patient craftsmanship, and truly holistic design. We live in an age of incredible power and speed, where we can calculate stresses to the micron and fabricate components across continents. Yet, in our pursuit of universal solutions, we often lose the conversation with the local, the specific, and the seasonal. The medieval master worked with stone from a nearby quarry, understanding its unique faults and strengths. He designed for the specific angle of the sun in that valley, for the particular flow of that river, for the known winds of that hilltop. His wisdom was place-based and therefore inherently resilient. As we now face our own monumental challenges of sustainability, resilience, and building for an uncertain future, perhaps the greatest lesson is to humbly return to these stone and timber teachers. They demonstrate that longevity is not just about stronger materials, but about smarter relationships between structure and soil, between form and force, between human ambition and environmental reality. Their buildings are not relics but active dialogues with time, showing us that true endurance is a kind of graceful dance, not a rigid stand. They remind us that sometimes the most advanced path forward is to rediscover a deeper, older way of seeing. If you found this exploration of lost engineering genius fascinating, we would love to hear your thoughts. Let us know in the comments which of these 25 structures amazed you the most. Was it the floating logic of Brunelleschi's dome, the silent breathing city of Derinkuyu, or the celestial alignment of the great cathedrals? Your curiosity fuels our journey. Subscribe to continue unraveling the profound and often overlooked mysteries of our past, where every stone has a story, and every story challenges what we think we know about human ingenuity.